much for inviting me. It was a pretty short notice, so I only learned about this presentation on Thursday. And I have a pretty well-polished talk, but I've already given it 4 times in different audiences, twice in Massachusetts. So I figured out, since I, as a student, really hate it, when you spend 2 years, come back to the talk of the professor that you loved last time and realize that he only changed 2 slides. So I don't know whether there is any overlap between this audience and the audiences that I have already given that old talk to. So I decided to put together a completely new talk based on the recent customer presentation that I made. And I was totally mystified by the word developer in the name of this event. So I made it very technical and very detailed. So if you want to hear more about whys, I have a talk that I given last year at GTC in San Jose, and kind of like gives the more general overview of our approach to machine learning. And today, it's more like an explanation of how we do it. And primarily, it comes as a response to a critique that we got several months back when we did the press release at Neurala talking about our lifelong DNA technology. And the main critique was, well, it's too good to be true, and they didn't publish in any serious journals, so that must be fake. Yes, we don't publish in the very serious journals. Why? Well, I have 4 PhDs on the research team aside from the founders, and we all have our publication records, and we know that it takes a lot of time between the moment you get the results and between the time you get the serious paper out. On the other hand, I only have 4 PhDs on the research team, and I'm running a startup here. I'm trying to stay ahead of the curve. Every time I have a choice between publishing what we already have or keep staying ahead of the curve, guess what I choose? But keeping the community in the dark is not what I intend with this policy. So I'm going to use this venue here today in order to provide all the technical details that we would have published if we had time for that, except for, well, maybe some secret sauce. That's another way to do it, actually, instead of publishing, and it's easier, because when the reviewer asks you, I want to see the math, there's nothing you can do. If you are asking me here, I want to see the math, I'll tell you, well, sign an NDA agreement. So this is actually from my previous presentation, just to set the context. Deep learning, which is so popular nowadays, is not AI, or not enough to be AI. Why? Because, first of all, backpropagation is a slow training method and requires a lot of data, and it cannot add new knowledge without retraining. That's the problem of catastrophic forgetting. I'm not going into details of this problem today, because it was pretty much well discussed in my previous talk. Plus, while TNN can outperform humans in individual tasks, they cannot beat our versatility. Because for versatility, what we need is quick adaptation, on the fly, on the edge. And we do have a device that is capable of this quick adaptation, fortunately, in our head. So the development of the technology that we do in Neurala is based on how the brain works. So what is the current state of AI? Well, we just have heard that the more data, the better, right? Massive amounts of data, large servers, millions of iterations for the backpropagation algorithm, and at the end, we have a neural network that is fixed, cannot adapt anymore. If you want to add something new, you need to get the new data, get the old data, combine them all, retrain for hours and hours and hours. So you are paying for the data collection. The biggest pain point that we encountered so far isn't even the collection, but the tagging of the data. Then you pay for the servers where you're running your training jobs. And finally, at the end, you get something that you cannot improve any further without repeating the whole process again. So if we symbolize this conventional DNN on the left here, it takes a lot of time in order to train the network to the performance criteria that you have. And at the end, you need to retrain it. The purpose of lifelong DNN that we developed is first to train it much faster, being able to run the network with much fewer training samples. And second, if you need to add the data, you just do it without retraining on the previous data set. So now I'm going to tell you everything, how we do it. But first of all, the comparison chart. So we only need seconds in order to do the training, comparing to hours or days or weeks. We can continuously improve our performance. We can learn at the edge. The process is so lightweight that we don't need the server. We don't require storing the data, so privacy concerns are not an issue. And we need much fewer samples of the data in order to achieve the same level of performance. How? Let's look at two main parts of any DNN. It consists of the backbone that is pretty much the same for different tasks. I've seen segmentation networks, I've seen object detection networks, I've seen object recognition networks, all based on ResNet 101, for example, or MobileNet. The complexity here depends exclusively on the speed precision ratio. ResNet 101, large, very precise, but also slow. MobileNet, smaller, a little bit less precise, but much faster. And the primary job of this part of the network is to extract and organize the features of the data so that the head can actually do the job. The head changes with the task. The one that I have here in the cartoon is the object classification task, 2 layers, usually sufficient. If you look at the segmentation network or detection networks, they also do the bounding box regressions for detection, they do upsampling of the data for segmentation. So complexity depends on the task. And the primary job of the head is to solve the task. Now, let's step back and look where the innovation comes in the field of deep learning. First of all, there are architectural improvements, right? Inception, ResNet, exception, all those come up, SqueezeNet. Those are usually done at the universities at a slow pace, and those are the ones that get published. Then there are custom loss functions, sometimes done in universities, sometimes done in the companies, but that's actually the main source of improvement of already existing designs. Take much less time to develop, and it's also much easier to hide. You can publish everything because the architecture is exactly the same. Just say that you have a custom loss function, and that's why you have 5% better performance, and that's what I'm going to do today. Then there are also custom layers. You know, YOLO is pretty much one and only custom layer sitting on top of the conventional backbone that does the object detection in a single pass. Mascara CNN has multiple of those. There is a problem with those custom layers. If you actually look at how many forks of Cathy are there and what they differ in, you will realize that there are dozens of them. And every single one differs in 1 or maybe 2 custom layers provided. What's the trouble here? Well, if you want to combine the cutting-edge research from multiple labs or companies together, what do you need to do? You need to check out 3 different forks, merge them by hand together, make them play well with each other, and then maybe you'll achieve something. Not a very easy task to do. I've tried it. And finally, the 4th source of innovation is the meta-manipulation. Data augmentation falls in this category, but also people tweak the training procedures in order to achieve better performance. So how do those innovations are distributed in the network? Well, architecture improvements, they go primarily into the backbone and a little bit in the design of the custom heads for specific tasks. Custom loss functions primarily in the head. Custom layers also primarily in the head. And then the meta manipulations, either the whole network if you're dealing with the data, or again, the head. Why I'm saying all that? Because we are not going to talk about architectural improvements. In order to create LDNN, all you need to do is to tweak the head. So we'll use custom loss functions, we'll use custom layers, we'll use meta manipulation. We don't do architectural improvements here. Why are we only dealing with the head? Because lifelong DNN has a very specific task, and that's what head is responsible for. So we need to learn new information after deployment without sacrificing the previous knowledge. We need to work in both supervised and unsupervised, and maybe also in the mixed regime. And we want to reduce the number of required training samples without sacrificing too much accuracy. On the left here in the slides, I have the use case for one of our customers where the user takes the picture and the system, through unsupervised clustering, puts this picture in the category of the similar pictures. So all the settings manipulating images in this previously taken pictures that are similar can be automatically applied to the new picture. How do we build it? Well, first of all, we throw away the head that's there. But we can use any backbone with some limitations that I'll talk about in the next slide. And the backbone will decide, again, the same things: accuracy, size, and how fast the network is. Then we put on our custom head based on a couple or more custom layers depending on the task. If it's object classification, 2 layers is usually enough. If it's object detection or segmentation, more layers are necessary. Then we add several custom loss functions that are introduced at different phases of training. And finally, we are altering the training procedure in order to have those different phases of training. Now, I said we can take any backbone. There are some backbones that are better than others. Accuracy, size, and inference speed are important, but even more important is the feature quality that those networks can extract. And for comparison here, I have MobileNet and SqueezeNet. They're kind of in the same class of networks in terms of size and the inference speed, both designed for the mobile applications that we are interested in. What we found out when we were testing them in terms of feature quality, that in MobileNet, the lion's share of the work is actually done in the head, not in the feature extraction layers. So if you chop off the head and try to put a different one, the features are just not good enough for LDNN to work reliably. On the other hand, SqueezeNet, probably because of the squeezing of the information on the way, extracts very good features. So it's just sufficient to replace the head, and it's able to operate fine. How can we solve the situation for the networks that don't extract good features by themselves? We introduce our custom loss functions by regularizing the feature space. And then what was interesting, what we noticed, if you add this custom loss function to the SqueezeNet, it just blows. It cannot learn properly. On the other hand, MobileNet starts to behave much better, and we're able to use it as a backbone. So how the procedure goes: the customer comes in and picks the backbone, or we pick the backbone for them if they don't have preference. And we add our custom loss functions, and we retrain it on a large data set to get the feature representation. Now, it doesn't have to be the same data set that the customer will be using later, but it should have similar features. So if those are visual images, ImageNet is fine. If those are some kind of LiDAR, then probably LiDAR images would do better as the data set. The important part is that we need to have our feature representation sufficient in order to build on-device learning afterwards. Then we replace the head with our custom layers that allow on-device learning, and the meta module that actually monitors the training and helps us to learn better. And then we deploy. As the user walks around with the device and uses our system, the meta module is monitoring the training, and it triggers memory consolidation whenever it is needed. Now, what is memory consolidation and when it is needed? We know that DNNs overfit the data. The faster we try to learn, the faster they overfit. On the other hand, there are always some outliers that we don't want to throw away. We need to learn those too. And another thing is that DNNs, by nature, have a lot of redundant information in them. So what we started to think about is how we can use this redundancy to reduce the overfitting and keep the outliers. So we're monitoring the training, and whenever we have substantial changes or weights that we didn't expect, that pretty much means that we encountered an outlier. On the other hand, if we are starting to get too many points in the feature space that are too close together, that means that we're probably overfitting the training samples. The system monitors it, and as soon as it finds several cases when we're starting to overfit or several cases when we have outliers, it triggers the consolidation. How does consolidation work? We look at the feature space and we do the cluster analysis of the weights of this particular layer. And as you can see here, for example, some of the clusters are pretty sparse, some of the clusters are pretty dense. What would happen if you take several points in the sparse cluster, merge them into one point, and throw the other two away? You will lose information. On the other hand, if you do it in the dense cluster, you pretty much will not lose any information. Actually, your system will probably become better because you're generalizing better between those 3 points right now, rather than overfitting all 3 of them. And that's pretty much the technique that we're using. The thing is that we don't want to do it on the sparse clusters, so we need sufficiently dense representation, and that's where our feature regularizing loss functions come in handy, because they basically force the clusters to be tighter so that the consolidation can do the generalization better. Now, what happens if I have, let's say, a layer of 512 filters, and I find through my cluster analysis that 5 of those filters are so close together that I don't really need them? Well, I set one of them to the average of those 5, and I reset the other 4 to the random values, the way they were initialized originally when the network was created. Meaning what? Meaning that I'm still using the first filter to recognize the same 5 objects, but I also freed 4 more filters to learn new objects that I have never seen before. Okay. Now some experimental data. The setup is very simple, monist for now. And the protocol is that we pre-train the backbone on 9 digits out of 10. We don't use digit 3 for training of the backbone. And then we train lifelong DNN on all 10 digits in batches of size 10 with random selection of digits, meaning that I don't have all 10 digits in every single batch, but approximately statistically, if I present 5 batches, it probably means that each of the digits was presented about 5 times. NVIDIA GTX 1080 Ti hardware, NV-Caffe with cuDNN backbone, and custom CPU layers for our on-device learning. Multiple networks. So if you go from left to right here, you can see that the leftmost network is actually the smallest, 0.5 megabyte in size. Inference time 0.3 milliseconds. Only takes 3 hours to train. Percent correct, not so good for NIST. We increase the size by about factor of 10. Percent correct goes up. Training time goes up to 5 hours. Inference time is 0.6 milliseconds, still actually pretty good to run on the device. And the size of 7 megabytes is also pretty good to run on a mobile device. The second step to the rightmost column is where we add our custom loss function to achieve the feature consistency. Now, as you can see, percent correct went a little bit down, right? Because we're forcing the weights in the network to represent not only the original information, but also we want them to represent the original information in the shape, so to speak, that we want to use it. Training time also went a little bit up, while size and inference speed didn't change because the architecture is exactly the same. Now we create our LDNNs on top of those 3 networks. As you can see, the size doesn't change in each of the 3. The inference time doesn't change. What changes drastically is the training time. 26 seconds for the smaller one, 44 seconds for the larger. Yes, the performance is nowhere near the good range from NIST. We're losing about 1% in the best case. But on the other hand, it's 44 seconds instead of 6 hours. If you are not looking for something as important as medical diagnostics, maybe that's a good trade-off for you. So I try to design the metric that will be able to represent combined training time and the error rate, so I just multiply them together. Here, the smaller is better, and as you can see, LDNN is actually in a totally different league. There's no way to compare. The numbers are like 2 orders of magnitude different. But what it also shows here, interestingly enough, is that the feature consistency improves the quality of LDNN performance quite nicely for the larger network, so that actually it becomes as precise per unit of training time as the smaller network, despite that it trains much faster. So if we look in more detail at the performance, here is the network without the feature consistency, 97.9% correct. And as you can see, the 7 is called 4, much more than 3 is called 5. Now remember, 3 is the digit that we didn't learn in the DNN itself. It's marked here in green. So basically the problem here is that with not good enough features, we're still making a mistake in the digits that the network's supposed to know. Now if we switch to the feature consistent network with full feature regularization, the percent correct goes up, but also you can see that there are pretty much no errors on the digits that the original DNN knew, and the minor errors come into play just for the digit 3 that it never seen before. Now, what if we look at the training process through time? So what I'm showing here at the x-axis is the validation results after every batch. Every batch is 10 digits, so it's likely that right here we only saw each digit 5 times. So if the 44 seconds for the full training set of 6,000 images, but 50 images is enough to reach 98% correct. So basically you can learn everything in 0.4 seconds here. Now, yes, it's not 99.6, it is 98.4, but it is 0.4 seconds versus 6 hours. Now, what about memory consolidation? There is the 2 bumps in the plot that I show you, and the first I mark with the red, and the second I mark with the blue. As you can see, the first time consolidation happens, we actually lose about 2% of the performance. First of all, features are consistent in this network, right? We trained it with our custom function, custom loss function, so consolidation doesn't happen very often. Why? Because our features are already pretty well organized in space. We don't need to do consolidation that frequently. There are fewer objects that are outliers. Consolidation doesn't change that much in inaccuracy, and I would say that's a very good performance for the on-device learning, because basically what we're showing here, that the user who has this system on their phone can be pretty much sure that the system always will be within like 96, 98% correct range without dropping too much, no matter what the user tries to learn with this system. In comparison to that, which is the signet that doesn't have the feature consistency, so here we have many more consolidation episodes because we have many more outliers. The feature space is not organized as well. Plus, the clusters are sparse, so every time we try to do the consolidation, we actually lose the information. The first 7 times, which are marked with red bar, the accuracy goes down in each episode. But if you look through the plot, it goes down less and less, and at the end, the last episode is actually green. Why is that? Because we're getting more data samples, so there are more points, so the clusters become more dense, and eventually, the consolidation starts to show its bright side by working on those tight clusters. To make sure that that can happen the other way around, I'm showing the different data sets, CIFAR10 at this point, and features in the CIFAR10 are more consistent because those are all visual images. But on the other hand, the images are so small and there are so many outliers there that it is really easy to overfit. So here, the effect of consolidation is actually bumping up the percent correct. Why? Because they're already tightly clustered. Every time we do the consolidation, we reduce the overfitting, the performance goes up. So the main conclusions on consolidation: it requires high feature consistency in the backbone that we're trying to achieve with our custom loss functions, and using natural images it becomes even simpler, so it's easily achievable, and it can reduce overfitting and improve accuracy on the validation and testing set. Now, what it allows us to do, in addition to what I already mentioned, is what we call the brain melding. What happens when there are two users with their respective devices that are learning different things and they want to share the information? Now, in the slides I show it through the cloud. Doesn't have to be through the cloud, can be point-to-point connection. The procedure is very simple. We take those two heads and we stack them together. And then we run our consolidation on the stacked head. And after we consolidated it, the head knows the information from both of the users, so we can redistribute it back, and now both cell phones can recognize the objects that each of those two users have learned. Now, that was pretty much all I wanted to tell you in terms of the technology. And now I'll switch a little bit more to tell you about how we apply this technology. Is it actually playing? Oops. I don't think it's playing. OK. Then I'll have to talk instead of showing you. So one of our applications of this technology, what we call as Brain Builder, that is the system that uses AI in order to help you organize your data in order to train neural networks. We have been using this tool internally for about, I don't know, about 9 months, 10 months, in order to organize our own data tagging, shipping it to the companies that did data tagging for us. But now we are ready to release it to the world. The beta program was announced some time ago. You can still sign up for it because it closes on September 7th. And we have how many hundreds? Yeah, we still have 750 slots. That means that 250 are already taken, right? No, we have 750 total. We have about 200 left. Oh, well, 200 left. OK, so hurry then, because 500 are already taken. What it helps you to do, it will help you to tag your data in the semi-automatic fashion, saving a lot of time for your data taggers, and naturally shortens the cycle of the data preparation. The second product that we have out there is our deployed on-the-edge system that learns on the fly. In one of the major cell phone brands, it is used to improve the quality of the pictures that are taken by the cell phone. And in general, you can use LDNN for all tasks that we are attributing to the deep learning. We can do object detection, object tracking, recognition, scene recognition, segmentation. For some of those, we have the system already completely developed and ready to deploy it. For others, we're in the prototype stage. So, for example, for image segmentation, so far we can only do the static. We don't have the fully developed lifelong DNN version, but it is under heavy development right now. And that reminds me that we need hands. So we're also hiring. We cannot offer you the salaries that Amazon can. But what I can promise you, that we'll pay you much less, but we'll demand from you much more. So it will be much more fun to work for us. A little bit information about Neurala. We are backed by primarily Pelion Ventures with some other investors all over the world. We received multiple awards and have a lot of media coverage thanks to our marketing people that are constantly trying to do things for us. Thank you very much. Any questions?
I like that because I saw Andres taking notes. And he's one of the smartest guys I know. So if he's taking notes, it had to be a good session. I had no idea what was going on. Questions? Oh yeah.
I was having trouble understanding what you meant by feature consistency. Is that because of your custom loss functions? Can you explain what it is again and how you achieve it?
Yeah, so basically, if you chop the head of the neural network at a certain point, and you look at the activation in the last layer there, it's supposed to represent the features of the object, the pretty high-level features by the time you are so deep in the neural network, right? So let's say you have a cat and a dog. If you want to do fast learning, what you are looking for is that the features at this layer that represent the cat will be sufficiently separable from the features that are representing the dog. So in some networks, that is true. In some networks, that is not. So what we're trying to do with our custom loss functions is to actually pull apart different classes so that they are tightly clustered in terms of the features for particular objects without too much overlap between the clusters.
Hi, I'm hoping you can speak a little bit more about how you do your real-time learning, right? As opposed to trashing the training set like we often hear about and retraining from scratch every time. Is this due to the consolidation that you're enabled? Is that you're training on that?
So basically, we have the custom layer where we set the learning rate very high. Now, the problems that come with it is overfitting, and to solve these problems, we're using consolidation in order to reduce it. But basically, it's just a custom layer with the custom learning rate that trains very high and is able to adapt really quickly. And since the backbone weights are actually fixed, we don't backpropagate them down. We're able to do it. By the way, we are thinking about the technology, but that's like further down the road, maybe next year, so that we can actually make the weights of the backbone also trainable during the fast training. But that's still at an early research phase.
So say my model goes off the rails for some reason, like I get suddenly a lot of pictures of kittens, but I want to be able to recognize that these belong to you. And I roll back my model to a previous version, and if so, how can I tell the difference between what that version was doing versus what version 3?
Yes, so the question is, if you learn something fast but wrong, how do you fix it?
And how
Right?
do you know that the other model was better? Like, how do you know what the difference is?
Okay, in terms of how do you know that the other model was better, it's probably the reason you notice that you've learned something wrong is when you see the performance of your phone that you don't expect, right? So you know it was working, you know that it was working fine yesterday, you know that it doesn't work fine today. So, and that is actually a very good question because this feature is not on my desk as a research leader, it's on our engineering desk. We already can, we just need to finish the implementation to actually so that you can pinpoint, okay, yesterday at 7 p.m. I did a training session that messed up the system. Why won't you forget everything that I learned yesterday at 7 p.m.? Or if you want to be more specific, yesterday at 7 p.m. I learned a lot of kittens, but I want to throw them away. Can you do it? It's basically you send this query to the system and it drops this particular piece of knowledge while preserving everything else.
So my question is about the slide where you showed that there are two users searching for some things, and then you're combining what they searched for, learning there, and then redistributing. Yes, the brain melding. I'm curious how much of Neurala's concern is about preserving user privacy.
very good question. Here's the thing. We don't share the data, right? Because the data is down here. By the time you get to high-level representation that exists in the head, those are just features. And even if you downpour them through the exact same network, you will not be able to restore the original images exactly. So we're operating in the feature space here, and this feature space is pretty much impossible to reduce back to the original data. That's why we're very happy that privacy is actually not our concern, because it's built in the system that we protected.